guess that's it. I should announce the continuation.
Right. Welcome back, everybody. I'm Ron Levy. I'm the other organizer, one of them anyway. And it's my pleasure to introduce, not to introduce, but to reintroduce our speaker today. Who's going to continue the series. The series, same rules. Please ask questions. But when you ask a question, raise your hand and I will come to you with a microphone so everybody can hear. And
thank you. Thank you for the introduction. Thanks to everyone who's here for coming back, and to everyone who's not here, well, you're not here. So I've been told that because this is the second day, questions are now worth $200 instead of $100. So right, so let's just remember what happened yesterday very briefly. We're talking about configuration spaces, which come in two flavors. There's FK, which is the ordered configuration space. It's BK, which is the unordered configuration space. And what we did was we calculated the integral cohomology of this space when X is Euclidean space of some dimension, and we calculated the rational cohomology additively of this space when X is a Euclidean space. That's what we've done so far. We also learned a lot of other cool stuff, but all of it was in service of those calculations. Okay. So what we're going to start with today is we're going to think about how we might be able to adapt some of the information that went into the calculation of the rational cohomology here to toward the task of calculating the mod P cohomology. Okay. So that's the goal initially. So a convention that will be valid until it's not is we're going to fix A prime P, which is greater than 3, just in order to make uniform statements. As we saw yesterday, things are different at the prime 3, and we didn't see this explicitly, but things are also different at the prime 2, as is often the case. And we're going to concentrate on the case where n, the dimension of the Euclidean space, is even in order to make uniform statements. The odd case is actually easier, at least initially, and then about the same, just scrambled. So it doesn't really matter. And from now on, again, until it's not, all cohomology is with FP coefficients. Okay. Is there a question? Sorry? Okay. Good. Okay, so the thing that we used for the rational calculation was the transfer, which realized the rational cohomology as the invariant part of the rational cohomology of the ordered configuration space. That doesn't work mod P, but there's a replacement, and the replacement is called the Cartan-Larrey spectral sequence. So first, let me tell you what the Cartan-Larrey spectral sequence is. So proposition. I won't give a general statement. I'll just give the statement in the example of interest, but it is a general tool. There is a spectral sequence that has E2 page given by the group cohomology of sigma k with coefficients in the cohomology of the ordered configuration space. And it converges to the cohomology of the unordered configuration space. Okay. If you haven't seen group cohomology, you don't need to know that much about group cohomology to follow what's going on. You might be soothed to know that group cohomology is the same thing as the cohomology of the classifying space of the group with twisted coefficients, perhaps twisted coefficients. In this case, they are twisted. And so we're thinking of this vector space as a representation of this group. And fortunately, from yesterday, we know a lot about that representation. Yeah. If you haven't seen spectral sequences, I'm sorry, there's a spectral sequence on the board. It will not be there for the entirety of the talk, so just hang on, and we'll get there. And maybe you'll learn something about spectral sequences, at least in a contextual sort of sociological way. Okay, so this is our tool. An exercise, if you know about the Serre spectral sequence, is to prove this, construct it as an instance of the Serre spectral sequence. It's not the one that you would think of first. It's the one you think of second. Okay. Great. So let's start to try to understand what the spectral sequence says. That's what this board is going to be for, if I remember to keep it here. So there's our spectral sequence. So far, this is what we know about it. We're doing good. Here's the S axis. Here's the T axis. And maybe I wanted to call this E2 of K, because there's one spectral sequence for every configuration space. So what do we know? We know that the T equals 0 rho, if we look here, T equals 0 is H0, which is just the ground field, trivial representation. And so we get the cohomology of the symmetric group, which we're going to just treat as a black box. So it's HS group cohomology of the symmetric group, aka cohomology of the classifying space, which is something that Nakaoka tells us. The S equals 0 column is just the invariant part over FP instead of over Q, but we've calculated that. Or basically we've calculated it, but we've calculated it. So it's H T, the ordered configuration space, the invariance, which we know from yesterday. So down here at the bottom, we have, I can't draw straight lines to save my life. We have HS of sigma K, filling out that row. There's infinitely much stuff, but it's okay. And in this column, if we remember what we learned, so I'm drawing a picture of E2 of K, where K is at least 2. When K equals 1, there's nothing there. What we learned last time is that the invariance, or what is implicit in our calculation yesterday, is that the invariants are very simple. There's just one invariant class. When n is even, there are none if n is odd. And it lives here. There's a copy of the ground field there in degree n minus 1. Okay. That's what we learned. And the rest of this column, I guess I can fill that in. Maybe I'll just say it instead of filling it in. The rest of this column is trivial. Okay. And everything out here is unknown. Everybody on board so far? Okay, so let's remember something, or if you don't remember it, it's an exercise. It's a basic fact about group cohomology, which is that when the prime in question does not divide the order of the group, there's no group cohomology. Okay, so if P does not divide the order of a group, then the positive degree group cohomology of G with any coefficients is 0. So for any representation of the group over FP. G is a finite group, of course, otherwise it doesn't have an order. I'm going to raise this momentarily. I apologize for writing so low, and then I'm going to lower it again. So again, what we are saying is that if the order of the group doesn't involve the prime, then there's no group cohomology of any kind, and we're just back in the previous situation of essentially of the rational calculation. Okay. So what that means is that the first interesting case where more than just this appears is when number of particles equals prime. Right? Yeah. Oh, let me finish the sentence. For any module.
Oh,
Yeah,
okay.
thank you.
That was-
Almost every other time, M will be a manifold for me, so it's good that you asked. Okay. Great. Okay, I'm lowering this again. Okay, so so we're going to put ourselves in the first interesting situation. Now we're going to put ourselves in the situation where there are p particles and see what happens. Cool. So let's remember that this thing, the coefficients of the cohomology of sigma k that we're taking, sigma p that we're taking, decomposes as a direct sum of representations indexed by partitions. That's what we spent probably for you an exhausting amount of time talking about yesterday. So that means that we can break this calculation out over that direct sum decomposition, one for every partition of P. Who are the partitions of P? Well, there are many of them, but only 2 of them matter. So, the lemma is that unless lambda, which is a partition of P, is that obvious partition of P or this obvious partition of P, the cohomology in positive degrees of sigma P with coefficients in L lambda. L lambda is the name of the sub-representation of cohomology indexed by the partition lambda. That vanishes. So what that means is that most of the stuff that you might have thought was there is not there. There's just some stuff for this partition and some other stuff for this partition. Okay. Everybody on board? Okay. Let's prove it. So let's remember what we know about this representation L lambda. We actually know that it is an induced representation. We proved that last time. So L lambda is induced from the subgroup sigma lambda, which is the subgroup that stabilizes the corresponding ordered partition from a tensor product of smaller atomic building blocks. Okay. Okay. Why is that good? That's good because there's something called Shapiro's lemma, which is another of the most basic results of group cohomology, which you can prove as soon as you know the definition and the Hom tensor adjunction. It lets us say something about the cohomology of induced representations. So, so Shapiro's lemma says that the cohomology that we care about, cohomology of sigma p with coefficients in L lambda, is the same thing as the cohomology of sigma lambda, the thing that we induced from, with the original coefficients, the thing that we induced up. Yeah. Okay. Okay. Well, if this was a direct product, then we could use the Kuna theorem to kind of break this up into tensor product factors. It's not quite a direct product. It's a product of Reith products, but it still will sit inside of that corresponding tensor product. And the thing to observe is that, or actually, I'm saying way too much. That's all true, what I just said, but let me retract it because it's unnecessary. Easy, the order of sigma lambda is prime to p, unless lambda is one of these two partitions. If lambda is one of these two partitions, then sigma lambda is sigma p, or it's sigma p Reith sigma 1, which is also sigma p. Okay. Otherwise, sigma lambda is a product of groups, each of which is sort of obviously relatively prime to p. So, so this is 0 by that fact. Questions about that? So I mentioned yesterday that I'm telling a lot of stories from Fred Cohen's work, and specifically from his thesis. So this story that I'm starting with today is one of the main stories of his thesis. And he, as I mentioned yesterday, has a number of named theorems in that work. One is called the invariance theorem, which we proved yesterday. This is also one of the named theorems in his thesis. He calls it the vanishing theorem. He doesn't prove it this way. He proves it a different way, which is more complicated. And so one of the things that I would like to convey during these lectures is that having a bit better control over what these representations actually are trivializes a lot of the work. So the invariance theorem was made quite easy once we had a little bit of a grasp of what the homology looked like. And this vanishing theorem is also made totally trivial once we understand the representation a little bit better. Cool. So what that means is we can update our picture. The partition 1, 1, 1, 1, 1, 1, 1 is this bottom row. And so there's only one other thing that could possibly be non-zero. We don't actually know right now that it is non-zero, but it could be, which is the top row up here. And what goes there is HS of sigma p with coefficients in LP. Okay, and this is in degree p minus 1 times n minus 1. And everything else is 0. Everything that's not indicated in one of these rows is 0. Yeah. Questions so far? Yeah. All right. So if we look at this picture, what we can see is that there's actually only room for 2 differentials. There could be a dn that goes like this. And there could be a long differential that goes from this top row to this bottom row. This is d p minus 1 times n minus 1 plus 1. Okay, that's it. That's all that could happen. So the question is, what are those differentials? Okay. So the idea to understand dn, you don't actually need. I'm coming at this differential in a certain way to introduce some ideas that we will follow up on in a little bit. So you could do this in a less in a different way. But the idea is that the source of dn corresponds to the partition, which is 2 and then 1s everywhere else. So this invariant shows up first for k equals 2 and then persists as this partition for all further k. Okay. And that partition comes to us from smaller configuration spaces, actually in two ways. This comes from smaller configuration spaces in two distinct ways. So one of them I will put under the generic title of maps out. So what are maps out? Well, in this case, we can look at the configuration space of p particles, and we can take those particles and we can keep them exactly the same and just regroup them and view them as first a configuration of two particles and then p minus 2 configurations of a single particle. This is we're just perverse this way. So this is a map to f2 times f1 to the p minus 2. Okay, so we can somehow break this partition apart into its pieces. Okay. Specifically, what's the map? It's just the coordinate projection, right? So, or you might say it's the identity, restriction of the identity. So it's x1 through xp is sent to the configuration x1, x2, and then the configuration x3, and then so on. Okay. Everybody on board? Okay. So this is an example of a map out. What about maps in? So what you can do if you have, a map in is going to be the other direction. It's going to go from f2 times f1 to the p minus 2 to fp. And what we have to do is we have to take a configuration of two particles. So it's, here's my configuration of two particles. And several configurations of one particle. Like maybe this one is down here. Maybe this one is up here. Oh, sorry. This has the name 1 because it's the only particle in that configuration. This has the name 1 because it's the only particle in that configuration. I'm stylizing Euclidean space as a box, but that's fine. You know how to make that identification. And what we can do is we can choose an embedding of each of the disjoint union of these Euclidean spaces inside of the larger Euclidean space, or Euclidean space. So here's Euclidean space also, and here's my embedded copy of this Euclidean space with its 2 particles. And here's my embedded copy of this Euclidean space with its 1 particle, which I will now call 3, and so on. Okay. So we just pick some pieces inside of the larger Euclidean space, identify them with Euclidean space, and use this to shove configurations in. Okay. Simple enough. Are there any questions about what these maps are? Okay. Well, then what you get with from these constructions, or one thing that you get is you get maps of spectral sequences. So we obtain maps of spectral sequences. They'll form the spectral sequence for p particles maps to the spectral sequence for let me not include the page number. So the spectral sequence for p particles maps to the tensor product of the spectral sequence for 2 particles with p minus second tensor power of the spectral sequence for 1 particle. These spectral sequences, there's nothing happening, right? We already said the first interesting case is p particles, so there are no differentials here. And this map is induced by, because we're in cohomology, the map in. There. And the map out gives us a map of spectral sequences back to the thing we started with. Okay. And what we can check really with only with the information that we already have, based on how we constructed these modules corresponding to partitions, how we constructed the cohomology, is that this composition, because we're looking at the partition 2, 1, 1, 1, 1, 1, 1, 1, this composition is actually an isomorphism on that spot in the spectral sequence. So because this invariant thing comes from precisely this product of configuration spaces, this composition is mostly going to be trivial, but it's going to be 0 in that spot. It's an isomorphism on a by degree 0, comma, okay. And then easy exercise, because we know that there are no differentials in this middle spectral sequence, this automatically implies that the differential on that thing has to be 0. Okay. So this implies that dn is identically 0. Okay. So so somehow the idea, the takeaway, is that the cohomology of the configuration space is assembled from smaller configuration spaces via these maps, and that places strong constraints on how the different partitions can interact with each other. Questions so far? Yeah.
Can I also do an argument where I change the dimension of the Euclidean space? to similarly get this differential 0, like include n-2 dimensional configuration space, do n-dimensional one into infinite dimensional one?
Not in any direct way that I know of. That would be mostly trivial because the degree of this cohomology class depends on n.
Yeah,
That-
but then the differential can't hit it because it would. If a differential hits something in the bottom row,
So maybe I don't understand.
I can.
I see what you're saying. Probably you can do that. Yeah,
Okay.
probably you can do that. Yeah. As I said, this differential is actually small potatoes. I'm only making a big deal out of it because I want to introduce these maps. This differential is the more mysterious one, or something. Yeah, you can probably do something like that. Other questions? Okay, so so the only possible differential now is this long differential that connects the top row and the bottom row. And we don't know anything about it because we don't know what is in the top row. We do know what's in the bottom row, even though I haven't written it down. It's been calculated, but the top row is mysterious. And so what we're going to do is we're going to exploit information about E infinity in order to determine that differential. Okay, so so we are going to use a bit of a priori vanishing on E infinity, namely the following, which is a lemma that I learned from the paper of Colel's. Really, this is a result of Nakaoka's, but the interpretation is Colel's, which says that the cohomology of the unordered configuration space is 0 for I greater than a minus 1 times n minus 1. Okay. And the proof is simple. So the configuration space is a manifold, so it has Poincare duality, right? And by Poincare duality, the cohomology of this manifold is isomorphic to the Kapaka-supported cohomology. And if we think about the Kapaka-supported cohomology is the same thing as the reduced cohomology of the one-point compactification. And if we think about what that means, well, the ordered configuration space lives inside of the Cartesian power, the k-fold Cartesian power. And compactifying that means adding a point at infinity, right? So that's one way to go to infinity in the configuration space is for a particle to zoom off to infinity. Its coordinate can go to infinity. Another way to go to infinity in the configuration space is for two particles to collide, right? In the Cartesian power, they can collide no problem and end up in what's called the fat diagonal, the union of all the diagonals. But in the configuration space, they can't. Those are the two ways to go to infinity in the configuration space. Coordinate goes very large, or particles collide. And so one way to say that is that the one-point compactification is, well, okay, so I need to get the shifts right. The dimension of this manifold is n times k. So if I was talking about the ordered configuration space, the one-point compactification would be the smash product of k copies of Sn, or in other words, also a sphere. And I have to quotient by the fat diagonal. So the fat diagonal is just the union of all the diagonals inside of this product. Okay. And then I also, because I'm talking about the unordered configuration space, I have to quotient by the action of sigma k. Okay. And this kind of space, this quotient by the fat diagonal, is something that is well studied. So Nakaoka, again, in a different piece of work, calculates the connectivity of this space. So the latter space, the right-hand space, is n plus k minus 2 that's not actually so difficult to prove, but it takes a little while. It's elementary means, and again, the Cartan-Larrey spectral sequence, but it's not something that we want to take the time to go into. But it's not mysterious. And if you feed this number into this expression and rearrange stuff, what you get is this. Okay, cool. So what does that tell us? If this cohomology must be 0 above this degree, then that means that E infinity must be 0 farther out than this diagonal. Because what appears on E infinity is the associated graded for the deduced infiltration on cohomology. And if we look, that means that everything to the right of precisely the diagonal that differential is talking about, the leftmost of those differentials, has to vanish at E infinity. Okay. So in other words, to avoid a contradiction on E infinity, all of those differentials have to be isomorphisms. So to avoid contradiction on E infinity, it follows that this differential d p minus 1 times n minus 1 plus 1 is an isomorphism in every degree. So what we have is sort of a periodic family of differentials, periodic because the cohomology of the symmetric group is periodic, going out forever this way. Yeah.
What happens in the fiber line? I mean, you didn't go above the dimension of pk.
What goes where? I'm sorry.
The fiber line, the p dimension p minus 1 times n minus 1.
This spot.
Yeah.
So that's the invariance of LP, and we calculated that was 0 yesterday.
Oh, okay.
Yeah, great, good question, good question. Yeah, this argument, strictly speaking, applies to everything to the right of that piece, but we know that that's 0. Other questions? Yeah.
So for the case where n is odd, we cannot go by the Poincare duality argument, right?
You need some other argument, yeah, or an enhancement of the Poincare duality argument, yeah.
All right.
Yeah. So implicitly, to clue everybody in, implicitly, we're using orientability when n is even, which fails when n is odd. So just since other arguments, those differentials are supposed to be parallel, but they don't look very parallel. Sorry about that. The argument in Cohen's thesis is different. He uses an argument that uses Tate cohomology and Swann's theorem on periodicity, which is a beautiful argument. It's more involved than this, but it brings in a lot of beautiful algebra. So corollary, we now know exactly what the spectral sequence does. We've determined it. We can calculate the cohomology of the configuration space of p points with fp coefficients. and it looks like an exterior algebra on one generator, which I'll call alpha, which is in degree n-1. That's this invariant class here. And then the only other stuff that survives is a truncation of the cohomology of sigma p up until it's killed by this differential. So that's to say that we have to cross over fp with a cohomology in degrees greater than p minus 1 times n minus 1. That's sigma. Or sorry, the quotient by that. So cohomology of sigma p modulo the ideal pi and f degree elements, which again is something that Nakooka tells us. Another thing that falls out of this is we have in the process of running the spectral sequence, we have calculated the top row. So part of the issue in understanding the spectral sequence is that we didn't know what that top group cohomology group was. Group cohomology of sigma p with coefficients in LP. But now we do. So now we know that the cohomology of sigma p with these particular coefficients is the same thing as the cohomology of the symmetric group with a shift. So it's cohomology of degree I plus p minus 1 times n minus 1 plus 1. Cohomology of the symmetric group with trivial coefficients. You might not know why this is something that we should care about a priori. I'll say something about that a little bit later when I say more things. But suffice it to say for now that it is something that's interesting a priori. Questions at this point? Yeah.
Sorry, maybe I missed it, but in this first corollary, is that a statement about the ring structure as well, or just
Yes.
additive?
Yeah.
How do you rule out some kind of multiplicative extension between the?
I don't remember.
Okay.
Yeah, I haven't thought about that in long enough that I don't remember.
Okay.
But you can.
Okay.
Other questions? Sonder asked, is this an isomorphism of rings? I said yes. Sonder then asked, how do I know that there's no multiplicative extension on E infinity? I said, I'm done. Probably, yeah. Yeah, that seems like that's the answer I should have given. Good job. I taught a topics course at Harvard, and Sonder was in the audience, and he often was able to improve my lectures in just this way. So thanks for carrying on the tradition. Other questions? Okay, so I just want to say a little bit more about this spectral sequence for larger K. We actually don't know, it's an open problem to determine the Cartan-Larrey spectral sequence for general K. It's not an open problem to calculate the mod P cohomology of ordered configuration spaces. What Cohen does in his thesis is he takes this one calculation and he does a bunch of indirect stuff and uses that to calculate the cohomology for general K. But it would be super nice to have a calculation that is this direct for a general K, I think at least. Cohen says you could do that, but it would probably be hard, and then he does this indirect thing. But we do know something. So let me tell you something that we know. So I'm going to give you a definition first. We're going to say that a partition of K is P subordinate to another partition of K. P is the prime, of course. If I obtain lambda by splitting a block of mu into P equal pieces. So if lambda is obtained from mu by replacing some block of mu I, by mu I divided by P times. Okay. So in particular, that block would have to be divisible by P. I'll give you some examples in a second. Maybe I do that splitting process multiple times. So perhaps more than once. So let me give you some examples of P subordinate C. So P subordinate to P is the partition 1, 1, 1, 1, 1. That's the relationship that's relevant in the example spectral sequence. We could also equally take P and 2 and split that into into 2 and a bunch of copies of 1. Since by convention we write the partition in decreasing order. You could do this multiple times. You can take P squared and you can split that into P times. And you could split that any number of ways, for example, into P minus 1 P's and then P ones. And you could keep going. Okay. Is everybody on board with this idea of subordinacy? So the relevance to, well, what we're talking about is that all of the differentials in the Cartan-Lie spectral sequence, it turns out, reflect this relation of P subordinacy, just as this long differential reflects this first relation of P subordinacy. So the theorem that my student Dejo proved is that if a non-zero component of a differential in the Cartan-Lie spectral sequence for the configuration space of any number of particles has source mu and target, or I should say source indexed by mu. Target indexed by lambda, then lambda is P subordinate to mu. So the spectral sequence decomposes effectively into a direct sum according to the different sort of sectors of this P subordinacy relationship. And the proof is exactly the same, just more elaborate, as the argument I gave about this differential, using the maps in and the maps out to split the spectral sequence into these different pieces. As a corollary, one can immediately deduce a theorem of Aron and Mahowald. And what Aron and Mahowald prove is that unless K is a power of P, or 2 times the power of p. The top row of the spectral sequence, this cohomology of this symmetric group with coefficients in LK vanishes. So the cohomology of the symmetric group sigma k with coefficients in LK is trivial. It's an exercise to deduce this from this statement. It's almost immediate. It's inductive. Okay, here's this cohomology group again. Why do we care about this cohomology group? Why did Aron and Moholy care about this cohomology group enough to write an Invenciones paper about it? I'm going to say a bunch of words now. So this module is the kth Lie module, or a twist of it by the sign representation. And this cohomology is calculating the power operations for the spectral Lie operad in characteristic P. And so that's interesting in and of itself because spectral Lie algebras are interesting. But what Aron and Moholy used this for is to calculate the layers of the Taylor tower, the Goodwillie tower, in the sense of Goodwillie calculus, evaluated on spheres in the Vn periodic, category of Vn periodic spaces. And they show that most of the layers of that tower vanish using this vanishing result. Okay, and this is a difficult calculation in Aron and Moholy's paper. They sort of brute force it, but it just falls out of a modest understanding of the spectral sequence. Do I have any other comments? I think my only other comment before we sort of change gears is I think these spectral sequences are quite interesting and they're not fully understood. So some progress has been made, again, by my student toward a direct calculation of the cohomology by determining the spectral sequence. But in general, we don't know. We don't know what happens. Yeah.
These spectral sequences, there are operations, Steenrod operations.
That's right.
Right? And
Yeah.
you can, by using the fact that the excess condition forces something to be zero at E infinity, you can derive the existence of certain differentials. This is work of Bill Singer from 100 years ago.
So are you saying that this person looked at this specific spectral sequence,
No,
or
not
that
this
this is a
specific one,
technique
but
in
the-
general?
Say spectral sequences
Yes.
in general.
I completely agree. I think that would be a good direction to look in. I haven't done that. Cohen in his thesis does determine the action of the Steenrod algebra. That's part of what he does, but again, only for p particles. Other questions, comments? Okay, so I think now would probably be a good time to take a break. So let's resume at 3:38. 15 minutes from now.
And how many seconds?
0. Not when I said it.